Okay, how many people in this class have used BLAST or are familiar with BLAST? Most people. Okay, that's very good news. I am still going to go through some of the basics. If you have any questions, let me know. I can also point you to more readings about BLAST. But I figured a lot of biologists, this is their very first exposure to bioinformatics. And it's a nice place to start in this class. This will be the first actual real like bioinformatics-y thing we're going to do that isn't talking about the command line. So it's good. So today I actually want to start a little bit earlier, go back a little further than BLAST and give you kind of the underpinnings of how sequence alignment, how to think about it, and how it was developed. So we'll go through the basics of alignments, talk about dot plots, which seem like they're not important, but are actually super, super important for understanding how BLAST works. Scoring alignments, global versus local alignments, approximate alignments, and e-values. So those are all important concepts to get out of this lesson. So what's the point of sequence alignment? Why would we care to do this? We've got some DNA sequences or some RNA sequences. Why would we want to align them? You might want to know how similar are two sequences. And this is something that you want to put a quantitative measure on. We're scientists, we like to have robust statistical measures of things. How similar are my two sequences? Which residues correspond to each other? And these are important questions if you're thinking about evolution. How did evolution change residues and which ones were changed? Is there a pattern to the conservation or the variability of the sequences? And what are the evolutionary relationships of these sequences? So these are all questions that you would be able to address using sequence alignment. This is typically how you would visualize a sequence alignment. So let's talk a little bit about that. So we have a string A, not using nucleotides at this point. You think about it as just text strings. So if you have a string A, B, C, D, E, and a string B, A, C, D, E, F, a good alignment might be something like this, where we print A, B, C, D, E, and then we draw a bar. A corresponds to A. We have a gap in this sequence, so the B has now gone missing. The bar for C to C correspondence, D to D, E to E, and then another gap for F. So this is trying to illustrate our best guess as to how one sequence may have turned into another sequence or how they're related is that this sequence has a missing nucleotide for the B, the sequence has a missing nucleotide for the F, and thus we have visualized a possible alignment. Does that make sense? Okay. Many alignments are possible, but we really want to find the best alignment. So you can make an alignment of any type. Something like this is technically an alignment. It is not a very good alignment. So this is, if you saw this get spit out by a program like BLAST, you would probably think your software was broken. Again, because this is not showing us any similarities between the two sequences. So then the question becomes, okay, well, what about this alignment? If we say, okay, I see a CT up here and I see a CT over here. Maybe if I line those up, that'd be good. And oh, I've got some A's. Can I make those A's fit together somehow? Oh, and there's some C's over here. So you start sliding things around, trying to figure out how can I maximize the number of matching nucleotides. But that's not a quantitative measure of goodness of alignment. So what we really need is a way to examine every single possible alignment. Have we actually considered every possibility? And a way to compute a score that gives us the quality of that alignment. So that we can take one alignment versus another alignment and actually decide which one is better. So the way we do this is you have to go all the way back to dot plots. And this is an example of a dot plot where I took Neil deGrasse Tyson, I printed the letters across the top, I printed the letters across the side, and anywhere a row and a column have the same letter, I printed that letter in the column. So in this case, you can see Neil deGrasse Tyson, it always lines up perfectly along the diagonal because there's always share exactly the same letter. And then you get some sporadic, like S in this row and this column are both the same, so we print an S. So this is starting to show us if we had a perfectly identical sequence, we would be able to see this as a pattern and as a diagonal. So comparing the same sequence is, actually this is really good for finding repeats. So let's look at another dot plot where I have Neil, Neil, Neil compared to Neil, Neil, Neil. And again, we'll see this pattern of parallel diagonal lines showing us where repeats are. So this is a pattern that's easy to pick up, it's easy to recognize. And so when you have a diagonal that stutters to a different part of the graph, you know you're likely looking at a repeat or something that's been shifted. Here's an example with a smaller repeat where I took BAR Barbara McClintock versus BAR Barbara McClintock. And here you can see the repeat is just along those little diagonals. So that allows you visually, this is one of the original ways that people figured out how to do alignments and how to visualize how sequences were related to each other. Back in the good old days when you only have 2 sequences to align, and that made a PhD. We have left those days behind. But there was a moment in the 80s in which this was like cutting edge. So dot plots are also useful when sequences aren't the same. So let's look at a deletion. So we have Neil deGrasse Tyson versus Neil Tyson. We end up with a graph that looks like this. And again, we're looking for those diagonals that are going to show us where there's some similarity. So we see the Neil and we see the Tyson, and there's a big gap in between, but that helps us to visualize the fact that there's a deletion along the vertical axis. We can also visualize inversions. Any guesses what an inversion is going to look like? Yep, the diagonal going the other way. So now we see our diagonal going in a different direction. So again, just looking for those diagonals is helping us to start to line things up and see patterns. These are all fake examples, just using a few words, but you will actually see published papers that use this dot plot concept to visualize really large structural rearrangements between chromosomes or between whole genome sequences. This is an E. coli to E. coli alignment by a piece of software called SynMap, which is really nice. It produces these giant dot plots. And you can highlight, you can see an inversion very clearly. You can see an insertion where you got a little stutter. You can see a segmental duplication where you have those parallel lines. So these kind of large scale global dot plots are actually really nice for looking at structural rearrangements. Okay, in any case. So a dot plot is really nice for thinking about how an algorithm works to compare sequences, like kind of the main algorithm that we use. And it's also great for thinking about, once you construct a plot, how you can score that plot to determine if you're comparing one alignment to another alignment. How could you actually score those matrices and make a decision about which one is quantitatively better? And generally, the idea is the path with the best score is the best alignment. So how do we score? So the simplest scheme, it would probably be, we'll give you a point if 2 nucleotides match. We have an example alignment. We're trying to decide how good it is. Every time a nucleotide matches another nucleotide, we'll give it a +1. And every time it mismatches, we'll give it a -1. This would be the absolute most simplistic way to do scoring. So something like this, A matches A, great, +1. B does not match C, so -1. We end up with a total score of 3. So very simple. However, that's not actually based on biology. There are better ways to do scoring as far as biology is concerned and taking into account what we know about genomes and how they work. Nucleotides are not mutated randomly. Transition mutations are a lot more common. So A's will flip to G's and back much more often, and C's to T much more often than you get transversions. So one of the scoring schemes that we can build to reflect this that helps us determine, like, is this a realistic alignment? As to say, if the residue is the same, so A to A, we'll give it a +1. If there's a transition, A to G, we say, oh, that's not totally unlikely. We'll give that a 0. And if you see a transversion, like A to C, you might give it a -1. So that's one of the ways that we can start to try to actually reflect what we understand about evolution and how DNA mutates. Yes, that is in like 4 slides. So hold on, it's coming. Deletions and insertions are coming. That is also another thing you have to score. We're gonna do amino acid to amino acid next, and then we'll get to that. Okay, so amino acids are also not mutated at random. If they have similar properties, hydrophilic, hydrophobic, that sort of thing, they're a lot more likely to replace each other in a protein and have that protein still be functional. Evolution, again, selecting for these things. So instead of guessing what these rates might be, we can actually measure them empirically. This is Margaret Dayhoff from 1978. She was the one who, in 1978, was the first one to figure this out. The original bioinformatician that is kind of famous for this. We still use her matrices today in BLAST. And basically she said, I can go through and look at proteins between related organisms, determine their phylogenetic distance, and calculate substitution frequencies, and figure out how likely is it that one amino acid is going to turn into another amino acid. And she called these point accepted mutation, PAM matrices. And the first one was PAM1. So she would take 2 sequences, like real protein sequences from 2 different organisms that had an average rate of 1% amino acid change. And she would just measure in that 1%, how likely is it that one amino acid had changed into another amino acid. And she built this giant matrix with every amino acid compared to every other amino acid. And each column adds up to 10,000. So in 10,000, 1% are mutating out of the serines. Where did that, what did they turn into? And then she just counted. So that was pretty nifty. But PAM1 is only for 1% substitution, so it's not very robust across much longer phylogenetic differences. Proteins are often mutated by 20, 30, 40% and still have similar functions. So these compound over time. And so now we have, and Margaret Dayhoff continued to say, let's keep looking at things that are phylogenetically further apart. And now we have PAM30 and PAM70 are kind of the common ones you see, but you can generate PAM1 to 90. And PAMN just refers to, N is the number of mutations per 100 amino acids. This is PAM70. It is kind of, if you look at it, you're not going to get much out of it. So I turned it into a heat map. And it's kind of interesting. You can see kind of this light green diagonal. Amino acids are most likely to stay the same thing. But there's also a range of other things that they preferentially might turn into or might not turn into. Okay, great. So we talked about scoring. We have a scoring matrix. We can now use this to look up the serine turned into some other amino acid, and we can just follow the column and the row and find a score. And so we can give that a likelihood score. Do I think that that's likely biologically, or do I think that that's very unlikely biologically? The other set of matrices that we have are Heinekoff and Heinekoff. They did the BLOSSOM matrices, and that stands for block substitution. This is largely preferred over PAM today. They did a lot more work looking at divergent species and constructing lots of alignments and really refining this to be very biologically accurate. And if you go to BLAST, you can still pick the PAM matrices. You can pick a number of different BLOSSOM matrices, but BLOSSOM62 is the default in BLAST. So that is how the scoring is done when BLAST gives you an alignment. But like I said, if you're looking at to sequences that are much closer or much further apart, you can adjust that.
Okay. How often does the BLOSSOM matrix change? So if we were to go into BLAST,
never.
Never. So it's not something in papers that you would say we used in the BLAST and it was using BLOSSOM62. So that's not something that you have to do.
People don't generally change it. if you're going to change things in BLAST, it's usually word size, which we'll get to, or it's e-value. But you could, if you knew you were dealing with very phylogenetically closely related organisms, and you were a systematist and that was your thing. But for the most part, people don't mess with it.
So then in papers, it's not even mentioned unless someone changes that.
Yeah.
Okay.
So, and this is true of a lot of command line programs, and we'll see this in BLAST today. If you look at the parameters that you could change in BLAST, there are no joke probably 50 parameters that you can play with. So in a paper, I generally expect people to only put the parameters they changed from the default. And I'm going to assume the other ones are all default because no one wants to list all 50 parameters for every single piece of software they ran. In paper, your methods would get like completely giant. I don't usually see people messing with the matrix. Unless you're somebody who's really trying to dig into the evolutionary distance between two organisms and really optimize your alignments. In general, this Blossom 62 works pretty good for everything. Yeah. So in a paper, if you didn't change it, just say default parameters were used except for whatever you changed. That's what we do. Okay, gaps. So it's to Daniel's question, gaps, insertions and deletions. And this is interesting because we can also think about this from a biological perspective. A gap opening is more of a penalty than a gap extension. And the reason for this is when an insertion happens, sometimes it's 1 base, sometimes it's 5 bases, sometimes it's 10 bases. But the likelihood of that insertional event is one sort of statistical likelihood. The length of that is a different statistical likelihood. So the fact that an event happens, that's fine, but maybe the difference between it being 1 and 3 bases is not that statistically different. So we use the affine gap penalty, which is the fact that the event happened is a penalty of 11. We think that it's pretty uncommon to get insertions. So we're going to give it a penalty of 11. But as the gap gets wider, we're not going to penalize it as much. We're only going to do a gap extension penalty of 1 for each additional residue, whether that's a nucleotide or an amino acid. Does that make sense? Because it's not, I mean, if you penalized, let's say you had a gap of 1 and you penalize at negative 11, and then you have a gap of 2, well, that's not that much less likely. So you might penalize at 12 instead of penalizing at 22, which would be very unlikely. So it's sort of a scaled and affine gap penalty. So that's how we score insertions and deletions. So now we have a good way to score a particular alignment. You can look at your 2 sequences aligned to each other. You can walk down if the amino acid or the nucleotide has changed. You now have a way to score that. And if a gap is introduced, you now have a way to score that. And then you could take this alignment and quantitatively say which one is more biologically likely to be true. But that still leaves a big missing piece here. We still don't know how to generate all of those alignments. That is not actually a particularly easy problem. That is actually the hard part of this. The scoring turned out to be pretty easy, but generating all those possible alignments turns out to be quite hard. So in 1970, the very first that I know of sequence alignment program came out. And it was by Needleman and Wunsch, and it is still called Needleman and Wunsch. Not the most catchy of names, but it was a dynamic programming algorithm. And basically by dynamic programming, that's a method by which a larger problem may be solved by first solving small partial versions of the problem. So you could look at small parts of the alignments and build to a bigger alignment. So if you solve all these small problems and put them together, you can solve the big problem. Needleman and Wunsch is guaranteed to find the optimal solution. It is exhaustive. It will try every possibility. Many alignments may give you the same score, so you don't always come out with the best answer. You can have 2 answers that are equally good. It is also extremely computationally intensive and slow. So this is a good example of where you can get the exact same score for an alignment. If you shift the A and the gap back and forth, you're going to get the exact same score. So it's not perfect in the sense that it will definitely give you a best alignment, but it will give you the set of optimal alignments. You don't have to worry about it. I'm not going to actually make you calculate these. That's just kind of what the original paper looks like when it tried to explain how you take this dot plot and you plug in all the scores and then you follow it until you find the path with the best value. But you don't have to worry about actually doing those. So Needleman-Wunsch is a global alignment algorithm. So it is going to force the entire sequence to align to the entire other sequence. Local alignment became the obvious next needed step. Sometimes when you're sequencing, maybe you've sequenced this part of a gene and this part of a gene, and the overlap's only in the middle, and the ends, you didn't sequence those parts. Needleman-Wunsch can't really handle that very gracefully. It wants the beginning and the end to both be part of the alignment. So local alignment was the next big thing. And this is an example of if you force a global alignment, you can get one answer. But if you allow for a local alignment, which basically means I'm going to ignore the ends, you can get a completely different alignment. And if you think this looks a little better, maybe I just didn't sequence through the AV over here. In any case, local alignments can give you a completely different answer. I think I have another example of that here. Yeah. So Smith and Waterman came along. Their algorithm is also called Smith-Waterman. Very creative. In 1981. So they proposed a variant of the Needleman-Wunsch alignment algorithm to just do local alignments. Basically, the important part about this is there's no penalty for unaligned portions of the sequences at the end. So instead of counting every single one of these as a gap and subtracting one, they just give this a 0. Anything hanging off the end, we're just going to ignore it. It doesn't contribute to the score. And that's really important because if you take the same sequence and put it into a global alignment, you get kind of this big mess. If you put it into a local alignment, it will figure out that there is a large perfect substring in there. So you can get very different results by not penalizing these end gaps. Does that make sense? Still fairly time consuming. They made some important speed increases, which is good, but still rigorous. It's going to give you the absolute best scoring alignment by checking every single possibility. And at some point we had too many sequences in the world this was too computationally intensive. We couldn't afford to do an algorithm that would actually generate every single possible alignment because there's just too many sequences. And we needed a lot more speed. So now we rely on approximate methods. They're really good at detecting very closely related proteins. The closer, the better. Very distant relationships, we've lost a lot of power. Because they're approximate. They're going to try to guess at what the best alignment is and build on that. If that initial guess isn't right, you may have lost a lot of information. So the way this works is you start with words. So you start with little sets, little tiny collections of characters from the original sequence. In bioinformatics, these were originally called K-tuples. Now they're called K-mers. We'll hear a lot about K-mers over the course of the semester. And that's basically, it could just be like a former or a 4-tuple or a word of size 4, which is the AACT. That is a word that you can pull out of a sequence, or CTAA, or whatever it is. And they can be any length. This is an adjustable parameter for most pieces of software. And you take these words and you try to find perfect matches. So, let's say you have, what's the sentence you type that uses all of the letters of the alphabet? The lazy brown dog jumped over, the quick red fox jumped over the lazy brown dog. Let's say that was your sentence and you wanted to find some sequence similarity matches. You might say, okay, lazy is a good word. Z is pretty rare. We're gonna take lazy. So I'm just gonna go search this whole dictionary or this whole, let's say you're trying to find that sentence in a novel. You go in the novel and you look for all the instances of lazy. And then those are the only places you look for matches. That's an approximate, right? Like you're not actually going to scan the whole novel for every possible usage of every possible word in the original sentence. You're going to take one word, you're going to go into the novel, and you're going to look for that one word, and then you're going to look in the vicinity of that word and see if you can build the match from there. And that's going to save you a bunch of time because you're not going to try to look for every possible match. And that's essentially how BLAST works. This is called a heuristic. A heuristic approach is anything that employs a practical methodology. It's not guaranteed to be optimal or perfect, but it's sufficient for your immediate goals. And that's where we are today with pretty much every sequence alignment program. So BLAST stands for basic local alignment search tool. It was published in 1990. I think this is really cool. It was cited, it has been cited over 61,000 times as the most amazing. These authors have the most amazing H index of like any scientist you've ever met. It was the most highly cited scientific paper in the entire decade of the 1990s, which I think is pretty crazy. I got to be on a conference call with Webb Miller a couple years ago, and I was like, oh, hey, hi Webb, you know, like, because I just remember like reading these papers and being like really impressed when I was in grad school. And he's still a bioinformaticist and still active today. I haven't met the rest of them, but Altschul et al. 1990 is like, you'll see it everywhere. So that's cool. It was a very important paper, pretty much changed the course of bioinformatics. And the way BLAST work is, so these other algorithms I told you about previously, they were like you fed it one sequence as the query and one sequence as the match, and it was like a one-to-one thing, and it wasn't very fast. BLAST is really meant to take a query sequence and a whole database. They want like, my one query sequence, I want to compare it to thousands of other sequences and find the best match. And then BLAST really made that feasible for the first time. It will work on nucleotide or protein sequences. It calculates statistical significance. And most people who have seen this have seen it through NCBI, which is one of the most popular and biggest BLAST servers. And you can search just a plethora of data in NCBI. BLAST is divided up into a bunch of different programs. So if you go to the NCBI page, it looks like this. But I'll show you, here's the chart. If you have a protein query and a protein database, you use BLAST-P. If you have a nucleotide query and a nucleotide database, you use BLAST-N. And if you have, and there are some special ones that will take your nucleotides and translate them to proteins. And I'll actually try to translate all 6 frames and then compare it to a protein database. So anybody have any thoughts as to why we would want translated? Why would it be better to use a translated sequence instead of an original nucleotide sequence? Well, this won't actually get rid of the introns. It'll just attempt to translate the entire sequence as one giant open reading frame. It won't drop. It won't. I don't think it's smart enough to do like splicing. It just assumes you've given it something that's coding. It's not very smart.
Oh, so it just changes the intron sequence of the protein?
Yes, whether there's an intron in there or not. Yeah. Hmm? You're getting closer. Who else said something? Somebody in the back?
Someone said that it would be much shorter.
No. So 26 or 20 letters, like all of the amino acids, are so much more specific. With nucleotide, you only have 4. So it's really like you have a 1 in 3 chance of randomly, or 1 in 4 chance of randomly getting the same nucleotide because it's 1 in 4. If you're looking at amino acids, it's a lot more specific. It looks more like human language. Like you have a lot more information to do your alignments. It also gets rid of your wobble bases, so your codons that have synonymous substitutions. This can really trip you up evolutionarily because they happen all the time. And if you get rid of those synonymous substitutions and you're only seeing the amino acid, that's what biology actually cares about. So you're kind of getting rid of some extraneous information that isn't helping you detect evolutionary significance. So yeah, I like the shorter answer, but the problem is it takes that nucleotide sequence and it translates it into all 6 possible open reading frames and then runs each and every one of them. So the gain in making it shorter, you totally lost by just giving yourself 6 jobs instead of 1 job. Yeah, so that's why like protein blasts are so much more significant. You can detect sequence similarity down to like 30% of your amino acids have been retained as the same, and you can still say these are evolutionarily related proteins. At the nucleotide level, that's really difficult. It's more like 60, 70, 80% similarity to really detect these things came from the same original sequence. So yeah, proteins just have like a lot more information in them. We'll be using the command line tool. I'm sure you guys are shocked. But it's cool because it's ACF has BLAST installed, and you can do, I mean, we regularly do 50,000 genes from an organism, and we'll blast it to 3 million proteins just to try to functionally characterize them. So you can scale up to really big blast jobs. Here's a little bit more about how this works under the hood. So just to try to bring it back to why I went through all that stuff about dot plots, which are probably like, why is that significant? This is how you think about BLAST. You have your probe sequence, you have your database, and it'll actually just put like every single one of your database queries in one giant long row. And then it'll take a word, so this former. It'll take many words from your sequence, but let's say the first time you're just gonna start with one word, like AAAT. And everywhere it sees a match, it highlights it. So you get these little diagonals, right? The little diagonals that say, oh, look, I have a match between my query and my database. From there, the computer program goes through and it tries to expand those diagonals. And this is where it's gonna start accepting, well, what if I put a gap in? Well, what if I put a deletion here? Well, what about if I penalize this and let there be a mismatch? And it starts trying to build those significant alignments. But it only does it by, it's kind of priming off of that original word that matched perfectly. And then eventually, and it starts inserting gaps and stuff, but eventually you get a series of scores for all of these alignments that BLAST thinks, oh, this is probably a pretty good alignment. This is the best one I found. This is the second best one I found. This is the third best one I found. And this is important. I don't remember if I have a slide about this or not. This is important because the size of your word matters. If you pick a word size of 30, that means you need 30 bases to be exactly identical between your query and your database, or the alignment never gets seeded. If you pick a word size of 4, you only need 4 bases to be exactly identical between your query and your database. So it'll be a lot more sensitive. So this is how you control sensitivity in BLAST, is word size. This is the #1 parameter you're probably going to want to alter. The trade-off is, if you pick a very, very small word, your BLAST will take a very, very, very long time. So trade-offs. This is in amino acids. Words are going to be much more unique. There's lots of amino acids to choose from. Shorter word sizes are the default, and they're much more sensitive. For nucleotide searches, you want much longer, more specific words to seed your alignments. Because otherwise, like if you did use something like AAAT, you're just going to see that all over the place in your database. And then it's going to have to check all of those alignments, and it's going to take forever and a day to finish. Another good thing to note about BLAST is it doesn't give you, between one query and one database sequence, it will give you multiple hits. So it will say, I found one high scoring pair here. I found another high scoring pair here. I found another one over here. They can overlap. So it'll give you lots of these little, because it's a local alignment. So we talked about global alignment, local alignment. BLAST is a local alignment algorithm. So it will give you multiple local alignments between the same query and database sequence. And people get tripped up by this. And each one will have its own unique score. So you can look out for that. So let's talk a little bit about significance. How do we, now that we have this scoring system, how do we know at the end of the day, what is the likelihood that you're observing true biological similarity versus random chance? And the value we use for that is an E-value, or an expect value is what the E stands for. That is the number of hits one can expect to see by chance when searching a database of a particular size. I will ask you what an E-value is on a test, so just get ready. Like everyone who uses BLAST should know what an E-value is. So lower is more biologically meaningful. So here's some example. If you have an E-value of 1, that means you're just as likely to find a hit that is random as you are to find one that is biologically significant. And this does take into account your database size. So if your database is very, very, very big, and you have 2 hits and your E-value is 1 for both, you can think, well, one might be random and one might be biologically real. An E-value of 0.2 is a 1 in 5. So a 1 in 5 chance that you would find a random alignment just as good as this alignment that you have in your hands. 1 e to the -5 is 1 in 100,000. That's usually the cutoff that I like to use if I'm searching really big databases, because I want statistically meaningful results. 1 e to the -9, 1 in a billion. You will get e-values of 0, which is essentially they've calculated it so unlikely that this would not be biologically real. They just put a 0 on it. So yeah, that's how e-values work. All right. Any questions? No? Dot plots, scoring alignments, Needleman Wunsch, Smith Waterman, BLAST, and e-values. Yep.
I do have a question. You were
Sure.
talking about the word or words that are used to see the alignments in BLAST. Is there like an optimal number? I know you talked about the size of the word, I guess, but does it go through multiple words? Or,
it does.
Or is there a
It
default
takes your
value?
query and it breaks it up into lots of little overlapping words. So it tries from the beginning to the end of your query. It tries. I think there's a step size you can set too. It tries almost every possible word as a seed. So it doesn't like do 7 and then skip to the next 7. It'll do like 7 and then shift 2 and do the next 7 and then shift 2 and do the next 7. So it does do lots of words to give you your best possible chance of finding an alignment.
And does it decide on the number of words depending on the length of the?
Mm-hmm. Yep, it just keeps trying the words until it runs out of sequence at the end. Yep, and I think the default for nucleotides is 11, and the default for amino acids, I can tell you off the top of my head. I think it's 11 for nucleotides, it's trying 11. And it does lots of them, so. And it's just important to remember, like, because it's heuristic, it's approximate, even if you had like a 90% similar sequence, but it happened to have a gap in the middle of every possible word, you would never find that alignment. You have to have whatever your word size is, you have to have a perfect match, absolutely perfect, with that number of nucleotides or amino acids, or else it won't see the alignment. So if you're not getting hits and you want to try adjusting your word size down, that can help you get more significant hits. That's much more commonly altered. Setting the e-value cutoff, that's the #1 most altered parameter. Word size is probably the next most commonly altered parameter. Matrices are fun, but less commonly. People don't usually mess with those. Any other questions? Yep. All right. Okay. So all of that is online. Yep. Okay, so now we're going to work on the practical, which you can click. This is not on software carpentry. This is something that I wrote up, so it's not quite as detailed, but I tried to put a lot of text. So hopefully that will be good for you guys to follow. No, I really don't want to have to look at myself this whole time. Let's open a terminal. No. Okay, so we are going to go ahead and log into the ACF. We may or may not have a lot of problems today with this lesson. I've been emailing back and forth with the ACF help desk for the past few hours, so we will see. Bear with me. Okay, so the first thing, everybody try to CD into the course directory. And raise your hand if that is still not possible. Oh, good. Okay, that's exciting. we are going to start, instead of working in your home directories, we are going to start working in the main course project directory. So the first thing we're going to do is everyone is going to create their own personal folder. So I'm going to call mine msatan1, which is my user ID. That is probably the easiest thing for you to call your home directory. Making something you'll remember, you'll be using it for the rest of the class. And then I'm going to do ls-l, and I should probably start seeing a bunch of other people's. And mine, so I have my permissions by default. Is that kind of weird? Look, most of y'all, oh, they're all different, which is really funny. Or maybe some people are moving ahead in the lesson. That's fine too. So let's all try change mode, go minus RWX. Okay, so what does the G and the O stand for? Group and other, and RWX. Execute. So hopefully what this is going to do is make sure that you are the only person that can get into your new project folder and mess around. So other people should not be able to overwrite or look at any of your materials. So we get this capital S, which is not something that I talked about, and not everyone got it. Maybe some people are still catching up, but I put a clickable link to go see what that is. But basically, this is actually going to be really convenient. It means it's not something that I've actually had a lot of experience with. We've never seen this on our server, so I think it must be an operating system difference between my server and the ACF. But I think it means that every file you create inside of this new directory will carry the same permissions as the folder. So when you create a new file, it will also be rewrite and execute only for you personally, and it will not by default have group or other permissions. It's called the sticky bit, I think. Like I said, we've never really dealt with it much on our server, but we'll see how it works. As long as you can CD into it and create files, that's the most important thing. Okay, so now I'm going to CD into my folder. Okay, so on the ACF, we are on the login nodes, right? We are not on compute nodes. We're on these like login nodes that are shared across the whole university. We've been doing all of our LSing and CDing and RMing and heads and tails on the login nodes. And I felt pretty okay with that because those are very simple commands. They don't take a lot of computational power. We were probably, as a class, not getting in anyone's way. However, today we're going to do BLAST. That is an algorithm that actually takes real computational power. We're going to do very, very tiny examples, but I still am going to prefer not to do it on the login node. But there's something to remember. The compute nodes do not have internet access. They cannot see the world. So anytime you have to download data from the internet, you have to do it on a login node. If you get on a compute node, which we're going to do in a minute for the first time, you won't actually be able to get anything as far as wget. So I'm going to copy the two commands that are next in the lesson, which is wget and two giant FTP links, because I don't want to type them out. And I'm just going to paste them in. And hopefully you're going to see like a little progress bar of equal signs that's eventually going to say 100%. Does anyone have any problems with that?
I'm having problems changing with my permissions. I can't access the old file folder that I just made.
Could you help them? Nirul is going to come help you. You can always do U plus RWX, change mode U plus RWX, and then give yourself back all your permissions. U, G, O, yeah. Okay, so let me do LS. Yay! I have my cow and human proteins. And let's see how big they are. Does anybody remember what the H flag does? The L is for long listing. What does the H flag do? Human readable. One of my favorites. So we can see that these are very small files. The cow is only 12 megs, and the human is only 156K. So these are extremely short. When you go to the FTP site and see by they have them broken up into lots of little segments to make them easy to download. So we just grabbed the first one. Okay, so now what we're going to try to do, and I don't actually know if this is going to work, is we're all going to copy and paste this Q sub command in here. So all of the commands that allow you to access the queue, the actual line, like get in line for a job on ACF, start with the letter Q, which I think is just a mental reminder that it's like a queue, like line. And we're going to ask for an interactive job, which means we want to have an actual shell connection to a compute node. You can also submit jobs that, like scripts that just go run without you being there. And it's kind of like the difference between, what's a good analogy? Like doing something yourself and sending someone else to go do it. It's this, we're saying we want to be there ourselves. We want to have a shell. We want to access that compute node, and we will tell it what to do step by step, versus writing down all the instructions and sending it off without you having to be present. So this dash I stands for interactive. We want a shell. We want to interact with that compute node. The dash capital A is just specifying our project for the class. So this is going to make sure we get on, there are some nodes reserved for teaching. They are less full than the rest of the cluster. So this is really important. Some of you may have this class as your default project, and you wouldn't have to specify this, but I don't know who has it as a default and who doesn't, and we're not gonna mess with that. So we're just gonna specify it every time. The debug queue, so there's lots of different lines you can get in. It's like when you go to the grocery store and you're trying to pick the shortest line to check out. On the ACF, there are many different lines. The debug line is the one that we're going to use in this class, and that just basically means we get very tiny instances, but we should get them very fast. And it's called that because people who need to debug their code, they just want a little tiny bit of computational power. They don't need like 40 cores and 200 gigs of RAM. They just want a very tiny amount of computational power to do some debugging. So that is the line, the checkout line that we're going to choose. Dash L is just giving some more details. The maximum amount of time we can get for a session on the ACF in this line is an hour. So we're going to request that full hour. If it kicks us out before we're done today, we'll just log back in. And we're going to say nodes equals 1 because we only need 1 node. You can request more than 1 node, but we do not need more than 1 node. So whether or not this works is kind of a big question to me. I guess I should hit enter. I'm going to give this at least a minute or two. Bobby said it should be ready about 3:30. So we'll see. If not, we'll just start doing blast on the login nodes and they can just yell at me later, which will be fun. Did it? Okay. Exciting. Hopefully mine won't take too long. I told them there were a lot of us and to free up a bunch of resources. I don't know how seriously they took me. Anybody else's go through? Yeah? Okay, good. This is promising. Are other people starting to go through, or is everybody just still waiting? Or so some people, they went through very quickly and other people are waiting. Have there been, like, in the past 30 seconds, have there been additional? No.
Okay. the folder. Like denied access.
All right, should I put LS account? Okay, so CHMOD. Was RWX. I actually didn't have time to try this. I should be good now.
But when I get home, we don't hear it.
Okay, so creators now start right here. Sorry.
Yeah, what do we need to do?
All right, just so I have a count, email to the help desk. Raise your hand if yours worked. 1, 2. Yours worked? Okay, well,
Does the number mean what number you are like in the queue if you're in line?
I think that's the order in which they're submitted, yeah.
Okay. And they're rated on that order.
Well, they're balanced. So people who pay get priority, and people, if your job is smaller and it will fit on a computer that's running someone else's job, or someone else has a bigger job that won't fit, you can jump ahead of you that way. Yeah, there's a lot of the scheduling algorithm is pretty sophisticated. But all right, well, we're just gonna make the login nodes very upset. Okay, so for people who are waiting, Control C. Do you wish to terminate the job and exit? Hit yes. And it's deleting my job. So that's unfortunate. But for those of you who it worked, you're welcome to stay on your compute node. For those of you who worked, if you type uname-a, what do you see? I see, so this is telling me I'm on a Linux computer called ACF Login 2. Anyone who actually got this to work? Do you get something else? Hopefully. What do you get? Okay, so that's how she knows she's on a compute node instead of a login node, because it has a name that isn't login. So, oh well, I will email the help desk after class. So if you type print working directory, hopefully you should still see that you're in the you're not in your home directory, you're in your project, the class project directory, and your personal directory. So if you're not, get back there. Okay, so let's learn about the module system. The module system is a really cool way for people who run big Linux computers and clusters to offer a lot of different software packages to all of their users. And basically, it's not all of the software isn't immediately available, but it's an easy way for you to kind of load access to that software. So if you want to see all of the software that's available in ICF, you can type module avail for available. And it's going to give you a whole bunch of different stuff. And some of these are bioinformatics. Some of these are physics. Some of these are chemistry. So all kinds of crazy things that everybody at the university has asked to be installed. It is a deep list. For our purposes, yay, there's BLAST. But if we didn't actually want to scroll through that whole list, you think you know the name of the software, you can do module avail BLAST. And it'll tell me, yep, I know about a BLAST. I know about BLAST 2.6.0.
Can you use asterisk to
Yeah. No.
No.
Yeah, it's not. That's sad. No. I thought it would work, but I was wrong. And that's kind of the problem is you don't always know exactly how it's spelled or what the full name is. So I end up usually just looking at the full list. But yeah. Okay. This is not the most current version, but it'll do. It'll be fine. So just because you can see it, you know it's available. What you have to do to get access to it now is actually load it. And the command for that is a module load BLAST. It doesn't really tell us anything, as the command line often does. It just does your bidding and it doesn't give you any feedback. So one way you can, good ways to check if you can actually access a program. Check the version and try to get to the help pages. So you could go online and look up the command line version of BLAST and figure out that the flag to look at the version is -version. And oh look, I have access to BLASTN. It's telling me BLASTN 2.6.0 and gives me the build date. I can also look at the help pages. So when I hit enter on this, it's gonna scroll like 4 pages of text across the screen. Too fast to even see. But now you can scroll up and look at all of the many flags that you can change for BLAST. Okay, so BLAST has all of these different subprograms. We kind of talked about this. There's BLASTN for nucleotide query to nucleotide database. TBLASTX is nucleotide query to nucleotide database, but does 6-frame translation of both. I look these up every time. The only ones I have memorized are BLASTN, BLASTX, and BLASTP. All the ones that have the translated, you know, I don't know. So I don't think you need to have those memorized. I'm not telling you to memorize those. You can always Google BLAST and find them really easily. But on the command line, they're also different. So you type BLASTN for the one that does the nucleotide to nucleotide, and you type BLASTP for the one that does protein to protein. So that is part of the command, just so that's there. Okay. So
once you download BLAST, then you have access to all these different versions.
Mm-hmm. Yep. These are all of the ones. So BLASTN, TBLASTX, BLASTX, TBLASTN, BLASTP. I think it also comes with SciBLAST, which I can't remember what that is, and Make BLAST DB, which we're about to see. So it gives you a whole suite of programs that come with the BLAST command line package. And I put in this lesson BLAST command line manual. Again, you don't have to read this beginning to end. I don't want you to memorize it. It's just a really nice reference if you're doing BLAST on the command line, and it'll tell you about all of the features. So if you're ever struggling with BLAST and you're trying to figure out things, this manual is deep, and you can get you can get a lot of information. But it'll tell you about the whole suite of software that comes with the command line, a BLAST program. So that link is available. All right. Okay, so we have not done less in this class, have we? Okay, so less is not on the practical, so just bear with me for a second. I'm gonna hit the up arrow to get the BLASTP-help. That all scrolled through really fast, and it was kind of hard to navigate. If you type to a command called less, this is, you remember when we did the manual and it took over the whole screen, and to get out you have to hit Q? Less is the same thing. So if you hit less, now we can use the down arrow and go through, and the up arrow to go up. And you can search by typing a slash and a word, and it'll actually let you search the documentation. And to quit, you hit Q. Let me hit Q, and that pops me back to the command line. So I'll do that again because that was pretty fast. I'm going to do BLASTP-help. I'm going to take that all that output that it's normally spitting out to the screen. I'm going to pipe it to a command called less. And less is just a program that kind of puts a little, it's like a little mini, it's not a text editor, but it's like a little bit nicer of a text viewer for your shell. And so it just kind of takes over the whole shell, and it allows you to up arrow and down arrow. You can also use F and B to go forward or back a whole page. So if I hit F, I can go through page by page. And if I want to search this documentation, I type the slash, and then if I want to look for the word word, hit enter, and it's going to start highlighting all of the words. And as we talked about with BLAST, you can alter the word size. So this was an easy way to find the flag to alter the word size, which is word_size. And there's lots of other like very complicated flags that you will probably never want to mess with. And Q will get you out of that whole less system and get you back to your command prompt. Okay, so if I do an ls now, both my database files are gzipped, so let's unzip them. The command line to unzip files is gunzip, gunzip, star gz. So I'm saying gunzip everything that ends in gz. And now if I do an ls, I don't know how many of you guys have the color changes, but red meant compressed, and now I have files that are not compressed, so they're white again. So the files are ending in .faa. This is not, this is actually, these are FASTA format, but NCBI uses the .faa extension to tell you they are amino acid FASTA format. And I'm trying to think, I think they use .fan for nucleotide. I can't remember. But let me do a real quick thing on what FASTA is. Okay. FASTA format. This is one of the most common ways that sequences are stored in a file, so a text file. It is usually .fasta. In this case, it's .faa, but usually it will be .fasta. So the rules of FASTA format: a sequence must start with the header line. The header line must begin with a greater than. And even though this is wrapped on this slide, there is no actual new line. It is one single line, must contain your entire header, and it must begin with the greater than symbol. The first white space delimited words, so the first set of characters that are not white space, must be a unique identifier. Within that file, it should be unique. And then the rest of the line, you are free to put descriptors. So at NCBI, they put a description of the gene, and then they put the organism in brackets. None of that's required, but it's fine. You can put any sort of commentary on the rest of the line after your greater than, and then your unique identifier, whatever comments you want to make. You don't have to have comments. You can have a greater than and then just a unique sequence name. That is also okay. But that header line must always be there for each individual sequence. Below that, the header is followed by the sequence. It can be amino acid, it can be nucleotide. They're pretty much the same for FASTA files, except for one is using the amino acid codes and one is using the nucleotide codes. These can be multiple lines. They can be, they can have new lines, so they can wrap, they can have hundreds of lines, they can have one line. Technically, according to the specification, there should not be empty lines anywhere in the file. The file should either be a header indicating that a new sequence is coming, or a sequence, but it should not be empty. It's pretty simple. It's pretty basic file format. Sometimes you see stars, which means like end of open reading frame. So a stop codon they'll put in as a star. But other than that, there shouldn't be anything else other than A, C, T's, and G's for nucleotides and your amino acid codes for your amino acids. Any questions about FASTA format? Okay. Not too crazy. FASTQ format, on the other hand, we'll get to that soon. That's when things get interesting.
So it kind of generates the file by itself. That's what having the exit file and the save item.
Yeah, so like if you were starting from like a spreadsheet and trying to get to a FASTA file, that's why I teach Python. Because the way I would do that is write a Python script to suck the data in and spit it out in FASTA format. Are there utilities, like command line utilities to do that? Maybe. I'm not aware of any. Normally, like sequence data should arrive in your life as either FASTA format or FASTQ format. I realize that is not always the case. Like occasionally somebody will email me like an Excel spreadsheet. I'm just like, what is this? This is not acceptable. This is not okay. But hopefully sequence data arrives in one of the standard formats, at which point there are command line utilities to convert between formats. If you start out with something wacky, like tab delimited, we would write Python code to fix that. But by the end of this class, you'll totally know how to do it. So you'll be golden. Yay. Okay, so going back to the command line. I have my files. They're unzipped. How many sequences are in each one? We're going to use a command called grep. For some reason, this semester, I'm going like way slower than I ever have in any semester, so we haven't gotten to grep or to find. I don't think we're going to make it to it. So it's the very last software carpentry lesson. For those of you who are interested, it is super, super, super useful. I may try to think about some way to like give people extra credit if they go through it and like take a quiz, because I'm so like disappointed in myself for not covering it, but we're going at a good speed. We're not, last year I got a lot of complaints that I went too fast, so we're hopefully not doing that this year. So on the fly, we're just gonna do grep. It stands for Globally Search a Regular Expression and Print, worst acronym ever. That basically just means search for something. And we're gonna search for, and the -c means count. And we're gonna search for the number of lines that start with a greater than. This is something that even if you don't learn about grep, you may end up just memorizing. Like, I think there are people in my lab who have used grep for nothing else other than this exact command, because this is the command on the command line that will count the number of sequences in a FASTA file. So it's super nifty. It's worth writing down. So this tells us that our cow file has 63,754 header lines. So it has 63,754 lines that begin with a greater than. Beginning with a greater than should indicate new sequence coming. That should tell us the number of sequences in our file. We can do the same thing for our human, which is only 1,486 sequences. Why are they different sizes? I don't know. This is just how NCBI had them broken up.
Okay.
Mm-hmm.
With the grep command, can you, oh, okay, sorry, I need to read this.
Yes, so
I'm trying to figure out the symbol.
yeah, okay, so the greater than symbol just means like you're anchoring to the beginning of the line.
Right.
So I debate every year if I'm going to teach regular expressions in this class. Regular expressions will change your life. They are amazing. They are wonderful. They are complicated. It's one of those things that I don't think you need to be capable on the command line, so I don't teach it. But it is something that like is so useful. And I just never managed to make it all the way to regular expressions. But that's what this is called. It's a whole set of rules about how you describe patterns in text. I want this symbol at the beginning of the line and this other character in the middle, or I want this thing at the end of the line, or I want the numbers between 0 and 3, and I want 4 of them, and then I want a dash, and then I want, like, you can just make these super sophisticated patterns, and then go search a text file for that exact pattern. So they're very powerful. They're really nice for informatics. They're nice for counting things. They're nice for extracting things. They're nice for reformatting files. But they're a big lift, right? Like, you have to just memorize a lot of stuff to get regular expressions working.
So what's the point of having
the quotes?
I guess? Yeah.
Yeah, it just sets off the regular expression from the rest of the command. Actually, it might work without those. I think I tend to put them just to make it, to me, a little bit more legible. No, it doesn't like that. Okay, so you need those just to say this is, okay, so if I take out the -c, basically grep is going to give me every single line that matches the greater than. And so I don't want to print 1,486 lines to my terminal, so I'm going to pipe it to head just so we can see what that looks like. Didn't that work? Oh. What did I do to my human 1 protein file? Okay, let me re-download it, because I don't know what I did. Oh, there it is. So see, I will just hit the up arrow forever and fine. Okay, so now, I'm going to overwrite. Yay. Okay. So head. But if I only want to look at the header lines, we're going to do grep pipe to head. And it's going to show me all of just those commands. So the -C gives me a count. If I don't use the -C, it'll just give you every single match, every single line that matches your regular expression. And that regular expression, the caret means the line starts with, and then the greater than symbol means the line starts with the greater than symbol. And regular expressions are something you have to, it's a deep dive, you have to do a lot of memorizing, but they're really powerful once you're good at them. We don't, yeah, go ahead.
Just to reiterate, the negative -C, 2 carets, you're counting the number of sequences.
Yep. So this one is just saying search. Grep is essentially a search function. Search this pile of text using this regular expression. This is the pile of text, and it's just going to give you everything that matches. If you put a -C, that means instead of giving me everything that matches, just count the number of lines that match and give me the count. So that C flag is the key for the count part. C for count. Yeah, and it's okay to just memorize the like grep single quote greater than, caret greater than single quote, because it's just really useful for FASTA files. Yep. Okay, so we are not going to use all of these. I suspected some of us may have been on the login node, and we don't really want to take down the ACF and get everybody mad over there. So we're going to take a very small subset of sequences. So,
I'm sorry, can I ask another question, I guess?
sure.
Okay, so I'm reading, so the regular expressions, it says here, the formal language defined search patterns. Is it only used within grep, or are there other?
Oh no, they're used everywhere.
Okay.
Python and Perl, and
Okay.
I mean, I use regular expressions all the time. VI, if you become like a VI or an Emacs person, like you're like, man, it was crap, I need a much better editor. Yeah, you'll get regular expression support and editors, and every programming language has regular expression support. It's really powerful. Unfortunately, the regular expression specifications between like the shell and Python and VI are all a little bit different, which drives me batty. But once you get comfortable with one, it's like 95% overlap between all those programs. There's just like a few little like gotchas that you'll have to Google, but yeah, they're everywhere and they're pretty awesome. Yeah. Okay, so I am just going to get something called cow.small.faa. So I'm just going to take the first 16 lines of cow.1.protein.faa and put it into cow.small.faa. So this is just a tinier FASTA file that we can use to check out BLAST. And we can look at our cow.small.faa in nano and see that we've got 2 sequences. Exit with Control X. I mean, these are the 2 commands, so. Okay, so the first thing you need to know about BLAST is because of the way BLAST sets up that whole word thing, BLAST needs to index your database first. It goes through and creates a super fast a set of files that allows it to look up words, kind of like an appendix. It's very much like an appendix. So you know how you have like a really big, thick book. You don't want to look up every word or read every word. You're looking for some specific word. You can go all the way to the back and look up an appendix, the word in the appendix. It'll say, oh, this word occurs on page 16, page 112, and page 400. And then you can go find it. So that's what, and one day this is going to stop working because people are going to stop having books with appendices because they just have searches on their computer. But that day hopefully has not come yet. Hopefully you guys have all seen an appendix. But that's what BLAST is doing. BLAST is creating an appendix of your database. So taking all these sequences and breaking them up into words and making a super fast way to look up those words. And this is part of what makes BLAST so much faster than if you were just taking one query sequence and one database sequence and then computing every alignment, move to the next database sequence. You know, if you have to do that a few 100,000 times or a few million times, it takes a really long time. So this little appendix situation makes it super fast. So to create the index, we say make BLAST DB -n. So the -n parameter is going to be the database file, the file that you want to use for your database. I'm going to give it human. And then -db type, you have to put either protein or nucleotide. I think it's kind of funny. I think Glass should be smart enough to figure that out, but it's not. So we're going to put prot for protein and hit enter. So you should hopefully see adding sequences in the added 1,486 sequences in a very short amount of time. And now if I do an ls, I have all these new files. So when it makes these appendices, or these indexes, they're actually called indexes, it makes these little .phr, .pen, and .psq. These files, if you move things around in different directories, these files must travel with the FASTA file. BLAST expects wherever your database file is, these little index files must go with it. So think about it like a book. You want the appendix to travel with the book. So if you move those to another directory, BLAST will not be able to find them. Okay, so let's run BLAST, finally, right? So our first flag is -query, so this is our query sequences. So we're gonna use cow, small. There's only 2 sequences, but you know, proof of concept, make sure it works. Then we'll use -db to specify that we wanna use our human.1.protein.faa as our database. This is taking cow as the query, human as the database. This will spit all of our results to the command line, but in general, it's probably better to have them in a file or they'll get saved. So the way to specify where you want the output to go is to say -out. Cow. I like to kind of give myself some information about what exactly is in this file. So I use really long file names, which can be irritating to type, but trust me, when you go back later, this is gonna make you very happy. And actually a better thing would be to put BLAST P. So cow versus human, BLAST P dot results dot text. Or we can put an underscore. So there, that's a really good file name, right? We know cow was the query because it's first. It was run against human, that was our database, and we're using the BLAST P program, and these are the results. So I put tons of relevant information into my file name. And I'm gonna hit enter. Fortunately, it was only 2 sequences, so it was really fast. Now if we ls, we should have a file called cow versus human BLAST P results.txt. Does everybody see that file? Yay, okay. So let's take a look at that in Nano. Don't forget about your tab complete. Your tab complete is gonna save you a lot of typing. So in this case, I just did nano cow underscore tab. And because the only thing in this whole folder that starts with cow underscore is that one file, it just finishes typing all of that for me. So it saved me like 30 keystrokes, which adds up. So by the default, BLAST gives you a ton of information. And it's very verbose, which is nice. It gives you a reference to cite. It's actually a newer reference than the vastly popular Altschul et al. 1990. That's okay. Keep going down, it tells you the database you used was called human.1.protein.faa, so it gives you some database statistics. That's nice. And then it's going to go through each query one by one, and all the queries are just piled up in one file, but it's going to say, okay, first query sequence we looked at, NP0011935303. So it gives you the entire FASTA comment line as your query, tells you the length, and then it gives you a little summary of all of the sequences that produce significant alignments. And I'm going to make this a little wider, see if that helps. Okay. So it says, oh, I found this database entry XP0052444978. It got a score of 37 and it has an e-value of 0.004. So that's pretty significant, right? 4 in 100, so not too bad. Then it gives you the next one. I found XP011 whatever, the isoform X2, and that got a slightly higher e-value, so it's listed second. So these are just giving you from beginning to end, like the most significant, the next most significant, the next most significant. And we can keep scrolling through a whole bunch of these. Okay, we got to the end. And they're giving us e-values all the way to 6.1, which means that is very insignificant. Like you would by chance find 6 other matches in this database of the exact same score. So to me, that would be very, like, I don't really want those results. So we're gonna see how to get rid of those results in just a minute. But for the moment, it's important to realize, like, BLAST will give you things that are not that significant. Like, it'll give you everything. So after your sort of short summary of like your little table of like this sequence with this e-value, it will give you the full-on sequence alignments. So for the same query, we're still on the very first cow sequence. It's gonna say, okay, the best match I found was this 978 Roquin 1 isoform X1. It gives us very specifically the score, the expect value, the identity, so the percent identity, the number of positive hits, and the number of gaps. And then it gives you the actual alignment. So here, this is a little different than what we saw in the lesson, but basically this will align. The plus means that the 2 amino acids are similar enough to be kind of believable as an evolutionary substitution. It prints the letter if the 2 amino acids are exactly the same, and it prints nothing if there's the amino acid has changed to something pretty unlikely. So plus means, okay, kind of likely. The letter means it's identical. So you can kind of scan, if you scan this middle line, it kind of tells you how are the 2 sequences similar. If you remember, I said it'll give you many high-scoring pairs. So here's another part of the sequence that also has a significant alignment. And these little numbers are giving you ideas of where these scores are occurring in your hit. So in our query sequence, from nucleotide 16 to nucleotide 57, that matched our subject sequence. I mean, from amino acid 16 to amino acid 57, matched our subject sequence from amino acid 9 to amino acid 51. Our next best little high scoring pair occurred much, much, much further in the sequence. So in the query sequence, it was amino acid 646 starting, and it matched the subject sequence of 779. So 2 high scoring pairs. Since it's local alignments, we have 2 very different locations that showed maybe some sequence similarity that we're interested in. Does that make sense? It's not, I mean, it's kind of like, it's very text-based. It's not pretty. Like the NCBI one gives you a nice little diagram, draws you a little picture. You don't get that with the command line one, but all the information you need is there. And you can keep scrolling through and all the alignments are there. And then eventually, you'll get to the next query, which is probably way down, like hundreds and hundreds and hundreds of lines down in the file. And I forget, is there a way to search in Nano? Let's try Control W, query. Okay, let's try Control W. I think it was query equals. Okay. So that got us to cow sequence number 2. And then you could go through and look at these e-values are really pretty insignificant, not very exciting. And if you go down and look at the alignment, is that any good? Maybe that's not actually related at all. Not a great alignment. Okay, I'm going to Control X to get out of here. Oh, in the lesson, I did have the pipe to less, so it is in there. I just did it early. So, e-value. This is a parameter we definitely want to learn about. And let's look at a different output format. That output format is really big and there's a lot of information. If you have lots of sequences, you're not going to want to look at it in that format. So let's try a few new things. So I'm going to type BLAST P, and then I'm going to do a / and hit enter. This is basically saying I'm not done typing yet. Hold on. Hold up, wait. That's all that means. It's an escape character and you're escaping the new line. So basically what I'm telling the shell is ignore the new line. I'm not trying to actually enter this as a command yet. Just wait, I'm gonna enter more. You'll see when I get done typing like all 5 lines, it's a really nice way to organize your command line so that you can read it. You put all the flags at the beginning and the values, the parameters after that, and it's much easier to read. So that's, if you're wondering what the heck is going on, that's what it is. DB human. And I'm going to change that to tab. We're going to get a new tab delimited output. Okay, so lots of new things here. I'm breaking up each parameter so it's on its own line so that it's much easier to read. I'm using the escape characters, those forward slashes at the end of each line before hitting enter to go to the next line. And that's what's allowing me to do that. And our 2 new parameters are dash e value, which is going to let us specify an e value cutoff. So it's saying don't give me anything greater than 0.1. I only want things lower than 0.1, which will be more significant. And I want to try the out format of 7. Okay, so now we can use our nano to look at this one. I named that tab instead of that text to differentiate. So this time it's a little less verbose, it's a little tighter. It also helps that I have fewer hits because we did an e-value filter and got rid of a bunch of that stuff that looked pretty insignificant. We still get some header lines. Gives us a little bit about our query and our database. It gives us a really short description of this tab delimited set of results. What are my columns? So the column is the query from your cow sequence, the subject, which is your database sequence, the human sequence, the percent identity, the alignment length, the mismatches, the gap. And then you have to scroll all the way over, make it a little wider maybe. So the number of gaps that were opened, so that doesn't tell you the total number of maybe individual amino acids that are part of a gap, but the total number of gaps that were open. The query start, the query end, so saying like from amino acid 6 to 14 was the match. The subject start, the subject end, the e-value, and the bit score. If you go down to an actual hit here, we see our subject is the NP, and then the human is the XP, and then we have all our statistics in a nice tab delimited format. So you can suck this into Excel and sort and play with it and do whatever you need to do. For the second one, our e-value was actually stringent enough that we had 0 hits found. So it got rid of all of them. And at the very end, it tells you it processed 2 queries, so you know that it finished, which is nice. All right, we're getting pretty close here. Let's try to power through and get, okay, blast P. Let's try a couple more new command lines, flags that will be okay, so this is some fun ways. You can make the blast output look many different ways. And one of the things you might have noticed from the last one is we got our 2 sequence names, but we no longer have the descriptions. Oftentimes I really like having the description, like I want to know what that protein is, the 0078921, like nobody knows what any of those are. So I want to add back in the rest of that comment line. And so I use this all the time, and I think it's really useful. It's basically saying I want my output format, I want to use the standard columns that come with output 7. And I want to add this S title, which just means the subject, the rest of the subject line, so the subject title that comes, the entire subject header line. So that greater than in the BASTA file, I want all of that. And I want to append it as another column. Again, to figure this out, it takes some digging through the manual, but this is the one I use the most often, so I figured it was worth looking at. So in this case, you have to scroll all the way over. These are quite long. But we should at the end see that it has now appended that full comment line at the end. So if I do put it into Excel, I can look at the comment line and know what it actually matched instead of just 0052444978. So that's kind of a nifty one to know. We're going to skip doing the medium-sized data set since we're on the login node. So if you practice at home and you can actually get your QSub to work, feel free to do the medium. I'm just going to replace it with the small for right now, just to so that we aren't taking over the whole login node. So yeah, blast P. Oh, we're going to do small instead of medium. Value. I'm going to leave that as 0.0. I'm going to leave that at 0.1 because I think the e-value I have on there, 1e to -5, would get rid of all of our hits. Okay, so this time the output format 6 doesn't give you as much information. It's even more compact than the last one we saw. It doesn't give you any of those little descriptor notes. It doesn't tell you the version of BLAST. It doesn't tell you any of that stuff. It just gives you the tab delimited output. Max target seeks is really nice if you're like, I don't really care about all of the hits. I just want the best hit. We're moving forward with the best hit, which is oftentimes what you want to see if you're blasting a really big data set. So the flag for that is max target seeks. And so if I open this up, I've only got one hit. I only had one significant hit for my one query, and it got rid of all that extraneous other stuff about how BLAST was run. So this is a super short, very compact BLAST output format. And so if we do BLAST P dash help pipe to less, and then I am going to search, so \out FMT, and go to the next one. So to go to the next hit, you hit N. And these are all the output formats, so you have lots and lots of options. And it tells you options 6, 7, and 10 can be additionally configured to produce a custom format. And if you keep scrolling down, it gives you all of the things you can add to your column, your tab delimited output. So if you comb through the help, that is how you would have figured out how to do all of this on your own without me showing you. And if you're interested in changing the word size, you can go in here and search for the word and figure out how to do that. And if you're interested in changing the matrix, you can go through here and figure out how to change the matrix and what matrices are available. So it's all in there in the help. If you prefer not to do it in the shell, you can always go to that manual at NCBI and look it up through there as well. Okay, so our goal is going to be to not just run this on the command line and Q to exit, but we're going to take 50,000, 100,000 sequences, divide them up into lots of little jobs, to be blasted against the same database and shove that all off on the ACF and let hundreds of cores go do all of that work. So we're not there yet, but that's where we're headed. And that's why learning how to do command line blast is so powerful, because you can scale up to really like vast numbers. So that'll be fun. That's where we're headed. Get excited. Do you guys have any questions? All right. If anyone wants to stay after and get help with anything we did last time or this time or the homework, feel free. And I will be here until at least 5. All right, thanks guys.